Hello students, here are some review topics for chapter 5. This is by no means exhaustive. This is going to be just selected example problems. Now, is there some chance that you're going to see some exam problems outside these topics? Possibly yes, but that proportion will be relatively low, and also the probability that you're going to see those kind of problems will again be relatively low. So let's stick to these. Okay, let's begin with some proof problems. First, the linearity. Let's script T be an operator defined by like this. What do you mean by operator? Operator, function, map, transformation, transportation, all those mean pretty much the same thing. It's a kind of function that's something one thing to the other. And basically in this case, it is sending a function y into another function. And another function is defined by these bunch of derivatives and then some multiplication and then some addition. And we have to prove that this operator is linear, which means you can separate the addition and we can always pull out constant multiplication. How do we do that? We can use the property of the derivative, and as a matter of fact, let's see. This property here, and okay, if you take the derivative, then we have this property, right? You can always separate the addition, and then we can always pull out constant multiplication, C1 and C2. So for derivative, it works out. Excuse me, I forgot this brace. Okay, now it's complete. For the derivative, it works. And if you repeat this, it works for second derivative. Let's change the second derivative. And the second derivative. And then if I repeat it, I'm going to get the third derivative, fourth derivative, and all the way at the nth derivative. This property will work for all derivatives, and that's basically what we do repeatedly. Here's the proof, and just put it into the definition, and this is what we get. Instead of y, we just put in c1y1 plus c2y2. And then how about the derivative? The nth derivative, you can simply separate them as first and second, and then we can pull out coefficient, constant coefficient c1 and c2, and then what do we have? We have this form. The students who already went through will recognize this as a linear combination. And that's going to be repeated again for n minus first derivative, n minus second derivative, all the way to second derivative, first derivative, and then this is zeroth derivative, or in other words, no derivative. So all those are done. And then what we can do is apply this distributive law and commutative law for the real number arithmetic, and then rearrange this computation like this. C1 times an, first function to the nth derivative, and then the second n minus second derivative, and minus third derivative, all the way to no derivative, like that. And then does the same thing for the second function. And then what do you get? This is just the t of y1, where t is the same operator, and this part over here is t of y2. So what do you get? We can separate these addition and constant multiplication. Just a use of some characters, that's about it. Theoretically, it's not that deep. Now let's talk about homogeneity, and why did it prove the previous problem? Because we are going to be using the script T as an operator. By the way, according to our textbook author is using L there, and L can be confusing because we are using Laplace transformation as L, and when that is not the case, then we sometimes use L for any kind of linear operator. Can be confusing, so I'm using T. Okay, all right. y1 to yn be solutions of the homogeneous equation. Okay, homogeneous linear equation. And prove that the linear combination c1y1, c2y2, c3y, and so on, all these added up is also a solution. So if I replace the c1y1 plus c2y2 plus and so on and so forth, at each of these derivatives, then am I still going to get 0 is the question. Then answer is yes. How do you prove that? We can re-express this entire equation by simplifying the left-hand side using the script t that I told you before in the previous proof. And this whole equation here can be reduced into t of y is equal to 0, basically. So this whole thing becomes the same as t of y 0 is equal to 0. That. So basically, t of y is equal to 0. And then what did it say before? y1, y2, y3, those are all solutions. So t of y1 is 0, t of y2 is 0, t of y3 is 0, all the way up to t of yn is equal to 0. They're all zeros. So how does it help proving that this is also a solution? Well, t of c1 y1 plus c2 y2 all the way up to cn yn, let's consider that. And then is this really equal to 0 is a question, because I want 0 here. The answer is yes, because as we proved in the previous problem, we can separate all these additions here, and then c1 y1. Oops, I forgot this character t here. Oops, come on. Okay, all right. c1 times t of y1 and then c2 times t of y2, c3 times t of y3, and so on, all the way up to cn times t of yn. Add them all up. What do you get? c1 times 0, because y1 is a solution of the homogeneous equation. c2 times 0, c3 times 0, they're all zeros. So we're adding a bunch of zeros? Yes, certainly. This whole thing is equal to 0 as well. So what did it just prove? If we have n solutions, then any linear combination, c1 y1 plus c2 y2 plus c3 y3 all the way to cn yn are also solution. The student who paid attention in class will remember the other way around is also the case. General solution can be written as c1 y1 plus c2 y2 all the way to cn yn, provided that those are all linearly dependent. Well, we're not going to talk about that proof here in this review session because that's far more significant. Instead, let's work on something simpler about particular solution. Now, no longer equal to 0, but in this case we have f of t. In that case, what do you have? Well, we can write the general solution as solution of homogeneous equation, yh of t, plus one particular solution, yp of t. And that is, okay, all right. This yh of t is a solution of homogeneous equation, so this left-hand side part, whole thing is equal to 0. Or if I use that script t expression, where is that? Script t expression, okay. This whole thing here can be rewritten as t of y of t is equal to f of t. This expression and that expression are equivalent. And how about this one here? It's equivalent to t of y of t is equal to 0 in this case. Let's see. Yp is a solution of this equation, which means yp must satisfy this, or in other words that. So I can rewrite this thing as yp, t of yp is f of t, where yh is a solution of homogeneous equation. This whole thing is equal to 0, in other words this, and yh satisfies that. So we can rewrite this one as yh of t is equal to 0. This one, and then that one. This one, which I'm highlighting in red, comes from here. This one, which I'm highlighting in blue, comes from there. And then in general, what we have, this is something related to this blue. And that's something related to red. And if you simply add them up, then all solution of this original non-homogeneous equation can be written like this. So it's a particular solution here, so this is one specific, and this homogeneous part will have a number of C's, C1, C2, C3, all the way to Cn. Most of the time you're going to consider second order differential equation, so you're going to get C1 and C2 only, and that's just for simplicity. As a matter of fact, if we had time and if we consider fourth order, then you're going to get C1, C2, C3, and C4 all coming from this YH. And this one is going to be something specific, something particular. Anyway, how do we prove it? Actually, pretty simple. All you have to do is take some subtraction, y minus yp, and then plug it into this equation there. What was our condition here? Y is a solution of this equation. Yp is also a solution of that equation, and this one is general, and this is one specific, but still they both come from the same equation. So if I put those into this left-hand side, this operator, what do you get? T of y minus yp, and then apply that property of this operator, the linearity, which we proved in the first problem. We can separate them. So T of y minus T of yp, and both are coming from this. So we have f of t minus f of t, so it's 0, which means T of y minus yp is equal to 0. Wait a minute. That means y minus yp is a solution of a homogeneous equation. This one. And there you go. Y minus yp should be equal to yh. And then with some algebra, flip it over. Equivalent to that, y is equal to yh plus yp, and there goes the solution. I wrote one more line here, where yh is a solution of the homogeneous equation, but I already named it in the problem set, so even if you do not write the last line, if you stop here, that's going to be perfect. I already specified it. Time for one more problem. Okay, let's talk about linear independence and dependence problem. Okay, I wrote this specific problem, and let y1 and y2 be real functions. Prove that the following statements are equivalent. Condition 1, c1y1 plus c2y2 is constantly equal to 0 for every t value for some non-zero real numbers c1 and c2, and there's a name for that. This thing is called what? Linear dependence. This condition A is called linear dependence. Now, linear independence means there should not be those kind of real numbers c1 and c2. This one says for some real numbers c1 and c2, but there should not be any non-zero real numbers c1 and c2. So if you have this kind of equality, then c1 and c2 have to be both 0. That means linear independence. And linear dependence means there can be some non-zero. Excuse me. I have to correct this. For some non-zero real numbers c1 and c2, excuse me. It looks very much like both are non-zeros. That wasn't what I wanted. So for some real numbers c1 and c2, where not both are 0. This is not incorrect, but too verbose and long, so let's write like this. For some real numbers, so okay, let me use some logical symbols here. For some, so okay, there should exist things like that. Okay, for some C1, 2, and not both of them are 0. Okay, I guess that's sufficient. In this class, all those characters are considered as real numbers, and we're not going to deal with some other algebraic objects in this course. So real numbers go without saying, so this is going to be okay. That means not both of them are equal to 0, all right? And that's equivalent to the second. Either one function is constant times the other, one way or the other. And the second is called collinearity. y1 and y2 are collinear, which means, well, collinear usually means in geometry, those two objects are on the same line. So if you just lift over into some functions kind of thing, then they are both in the same linear relationship. So that's where this term collinearity were inspired. But here at this level, you'll have to expect those as just two algebraic terms. This means collinearity. That means linear dependence. Now, which one is easier to use? In my opinion, the second one is much easier to use than the first one. And in order to use it freely, we'll have to prove that those two are equivalent. Okay, let's go. The proof of A implying B. If this is true, then that's true. How do you do that? Well, that is equal to 0, where not both C1 and C2 are 0. So if C1 is not 0, then you can divide by C1, and what you get, C2 minus C1 is well defined. That's okay. And consequently, flip it over, we can express y1 as some constant times y2. What if C2 is not equal to 0? Then divide by that, then we have C1 over C2 is well defined. So this fraction is well defined. Flip it over, then what do you get? We get y2 is some constant times y1. So either way, we are going to have some constant times the other function, one way or the other. Simple proof. How about the next? This is going to be a little bit trickier. Let's see. If C is not 0, in that case, we get y2 equal to C times y1, this one, or the other way around, y1 equal to C times y2. Let's consider these in two different cases. In first case, y2 is equal to C times y1. You can rewrite as cy1 minus y2, and what do you have? It's in this form. And then the other case, pretty much the same thing. So in this case, neither the C1 nor C2 is 0, so it's okay. Now, what if C is equal to 0? In that case, C is equal to 0. If this is equal to 0, then y2 is a 0 function. So we can write like this. 0 times y1 and 1 times y2. And 1 times y2, this is a 0 function. So 0 plus 0 is equal to 0. So what do you get? Both C1 and C2, neither C1 and, C1 and C2 are not simultaneously 0. One of them is non-zero. Same goes over here. So we have the proof. Tricky. But in any case, we successfully completed the proof.